In the last video, we developed representations of forces. We took a complicated problem, an image of some objects, and we reduced that down to something called a free body diagram that helps us easily work with the forces without having to worry about all the details of the situation. And another form of representation is a model. And a model just seeks to be as precise as possible when we're looking at how things are happening in the real world. We want to be able to replicate that in a model. And a successful model will take into account everything that we need to perform our analysis. So there's two types of models that we have for forces. So in the first case, if we have something that's not moving, if we have a box that's just sitting on the ground, well, there are forces that are acting on this box. For example, you have the force of gravity, which is pulling downward, and you have another force that is pushing upward. And the box isn't moving, and it's not sinking or floating, so it's just standing still. And we have a word for this when something is not moving and we're analyzing the forces acting on it. It's called a statics problem. Statics just means that it's not moving. Well, then the other case you can probably guess is when something is moving. So there's really two types. There's something moving that's not undergoing an acceleration, and there's something that's moving that's accelerating. So remember from Newton's first law, if an object is moving at some constant speed, but not accelerating, well, then there's no force acting on it. And it'll just continue in a straight line forever. So if a satellite is launched into space, and it gets up to some initial speed and has some velocity, it's just going to continue along that path until some force acts upon it. So we can have some kind of constant velocity. We'll say that this box is moving with some constant velocity v, but there are still no net forces acting on this object. So it's not accelerating. And we know from Newton's second law that force equals mass times acceleration. So if there's no acceleration, well, then there's no force, net force acting on it. There can be individual forces. You could have a force that's just like with the statics problem. You could have a force that's pointing upwards and a force that's pointing downwards. But if they're equal and opposite, well, then there's no net force. The net force is zero because this force plus this force, well, that's zero force. So even though this object is moving and it might have some forces acting on it, the net force is zero, so it's not accelerating. And the other kind of object that we would have or that we would have to consider would be an object that's accelerating. So this acceleration is happening on the box. We have some acceleration. It obviously would have some velocity if it's accelerating. And again, if we look at Newton's second law, we know that F equals ma. So if we have an acceleration, well, then you can bet that we always have a force. That's the case. That if you have an acceleration, you must always have a force. We know, of course, the mass in this case is not equal to zero. So we have a force. So these are the three cases. We have something that's not accelerating, that's standing still. That's called a statics problem. And then we have these two movement problems where something can be either undergoing acceleration or it can be moving at a constant velocity with no acceleration. So these two cases on the right-hand side, these are called dynamics problems. We will encounter both kinds of problems, and they're both useful, and you can figure out some interesting facts about how these things behave when we do some analysis. So we have statics and we have dynamics. So statics is not moving, dynamics is moving, either constant speed or undergoing acceleration. So a statics problem would look exactly like this box that we have here. We have two forces. We know these forces, they're adding up to zero because we have no movement whatsoever. You could have additional forces. You could have something that's pulling to the right, and you could have something that's pulling to the left. As long as all the forces sum to zero and there's no net force, well, then we have a statics problem. And the other problems then, well, what would we do? We could do the same exact thing with these other problems where we have a dynamics problem, we can create a free body diagram from any of these cases. And you would see in the case of, for example, constant velocity, well, you would have still a net force equals to 0. So you might have this up and down situation like we have, but we saw here that this is 0 force when we add these vectors together, but this whole object could still be moving with a constant velocity. Just remember, it's not accelerating because there's no force. And then the free body diagram of the accelerating object, well, you might have some constraining forces that aren't really doing anything. They're not causing it to accelerate. But then you would have some other force that's causing it to accelerate in the rightward direction. So there would be some acceleration, and we know also that there would be some velocity to the right because we have some acceleration. So here we have some net force, and that net force is going to be equal to this vector. There's no vector that's pointing to the left that's canceling out anything to do with this rightward pointing vector. So we start from some image, from some picture or some drawing of an object, and we go from there and we create a free body diagram. The free body diagram for the statics problem would be very simple. It's basically the same as what I have drawn above. But we start from an image and we work down to a free body diagram because free body diagrams are simpler. We can look at them and we can compare the vectors easily. So typically we'll start with the general equation in physics problems that we're working with, that we're thinking about. In many cases, it will be Newton's second law. So we might have Newton's second law, and we're starting from this. This is a fact of the universe. So we can comfortably say that if we have some F net, well, then there's a mass times an acceleration. So we start from this fact, this law of the universe, and then we make it more specific. We can develop a specific equation for a given object. So, for example, if we're now looking at a completely different object and, there's some upward force and some downward constraining force, so we know that these two are equal and opposite, they add to 0. And then maybe you have two forces that are pointing to the right, one that's really long, another one that is slightly shorter. And sometimes you'll see the vectors drawn side by side like this. Other times in other textbooks, or just depending on the preference of the person who's working the problem, you might have the vectors stacked on top of one another like this. You might have one vector and then a second vector. Either way is fine, just know that they're pointing in the same direction and they're going to add together. They're going to increase one another because they're in the same direction. So I could start from Newton's second law, and I know that I have multiple forces, right? So F net implies multiple forces. If you're just working with a single force, well, that's fine. But otherwise, we have to sum the forces to get F net. So you have to consider all of the forces. We can look at these two up and down forces here, and we can make the argument, well, these are canceling each other out. They're equal and opposite. It's a Newton's third law pair, and that third law says these are equal and opposite. And then what's remaining is these rightward pointing forces. So to write this out formally, the sum of the forces, it could get pretty complicated if you're not making some sort of geometric argument to eliminate some of them from the get-go. In other words, I might say, okay, well, I'm going to sum up all these force vectors, right? So these are vectors. And I have an upward vector. Let's call this, this is going to be F1, this is F2, F3, and F4. So F1 is pointing in the positive vertical direction. So if I say, okay, I really want to write out all these forces, which there's nothing wrong with doing this, well, I would have a positive F1 y hat, because it's pointing in the positive vertical direction. And then I have a negative F2 in the y hat direction. And I have a positive F3 in the x hat direction. And I have a positive F4 in the x hat direction. These are both positive, F3 and F4, because they're pointing to the right. Now, I made a geometric argument, so these are equal and opposite, and I'm left with just the x hat components. So the sum of the forces for this specific object, sum of the forces is equal to F3 x hat plus F4 x hat, and you could rewrite this as F3 plus F4 because they're both in the x hat direction. And this is the sum of the forces. This then is equal to mass times acceleration. So we could have F3 plus F4 in the x hat direction equal to mass times the magnitude of the acceleration in the x hat direction. Why do I know that this is in the x hat direction? Well, it's going to point in the same direction as the force. F equals ma, these are vectors. So if the force is a vector and the acceleration is a vector, then I know that the acceleration gets its direction from the force. So if the force is pointing to the right in the positive x hat direction, then the acceleration is also going to point to the right. So this is basically, this a is the magnitude of the acceleration. I could call it a1 if I wanted to differentiate it a little bit. I could give it a new name. So we see now that we have only components in the one direction. If I had components in the y direction, I would have to treat those separately. I would not be able to analyze those at the same time. When I had it in this vector equation, I basically see these y hat components and I think, okay, well, those, I'm going to have to do addition and subtraction and any kind of manipulation with these components just with the vertical components, and then I'm going to have to do some separately just with the horizontal components. You'd have to split them up. Okay, so that's quite a bit, but basically the idea is this. We start from some sort of image. It could be something like a box, it could be a person, it could be the entire universe, it could be an atom. And you start with some object and you define the boundary. What are we interested in? In this case, well, we were just interested in the boxes. There was no other object to consider. And then we work with a free body diagram. We take this image and then we convert it into something that's a little bit more simple. So these images become free body diagrams. Once we have those free body diagrams, then we can analyze the individual vectors. And we can start with a fact of the universe, Newton's second law, the fact that F equals ma. And then we can write, well, what are the sum of the forces? Like, what does that mean? That means literally to sum up each of the individual forces. I could have made a geometric argument with this example, and I could have said, well, this up and down component, these are equal and opposite. So I don't even have to consider those because F net in the up and down direction is 0. The only F net that is some value other than 0 is going to come from these rightward pointing forces. We can then analyze the forces and we can set them equal to the mass times the acceleration because that's what the net force is equal to according to Newton's second law. So we'll be doing this to solve problems. We're going to be using free body diagrams probably more than anything else that we've learned here in these videos about representation and modeling. Free body diagrams are really the key to successfully solving a problem, being able to take an image and break it down into its individual components that we're interested in.